In this video, we'll cover rate laws. Say you have cookie batch ready to be baked in the oven. This batch of cookies are laid out nicely in a tray and it will form into a product, which is the cookie, after you have baked them. But say you have 2 trays of the cookie dough batch ready to go into 2 ovens. So now you can make double amount of cookies much faster. But say you don't have 2 ovens, but you're just limited to 1 oven. If you're only limited to 1 oven, then the production, even though you might have a lot of cookie dough lined up, ready to go, you could only generate 1 batch of cookies. And that's because the oven makes it limited. How does this relate to chemistry? Well, in chemistry, the reaction of how fast a reactant can produce a product is determined, or most likely will be determined by the reactant concentration. This is when I can introduce a new definition called the rate law. And the rate law is just the mathematical expression how concentration of the reactant affects the speed of the reaction. So how much concentration you have of the reactant is going to determine how fast or slow the product will form. Say you have A and B forming into a product. If I were to write a mathematical expression of this rate law for this equation, it will look something like this. It will have a rate, it will have K, and A and B, and you see these exponent M and N. The A and B in bracket represents the concentration of the reactants. The M and N that's in the corner, those are not the coefficient in front of a balanced equation, but there's going to be a number there, and those are called reaction orders. Then you'll see that little k. That little k represents rate constant. The little k, the M, and the N, the reaction orders, are determined experimentally, and only through experiments are you able to determine this with for the rate law. Now let's put all of those materials and information to the side and do an example. Here, nitrogen dioxide and carbon monoxide is forming to nitrogen monoxide and carbon dioxide. Now it says this reaction is second order in NO2 and 0 order in CO at 100 degrees. What is the rate law for the reaction? So remember, rate law refers to this mathematical equation. So the rate law would be rate is equal to the constant K, and instead of A, we write NO2 we don't know what the reaction order is, but actually it says right here, second order. So we put to the second power, and the 0 order for the other reactant, which is the carbon monoxide. So there is 0. No matter what concentration of CO is, since it's in the 0 order in the exponent of 0, it's always going to be 1. Just punch it into your calculator. 5 to the 0 power, 100 to the 0 power, 1,000 to the 0 power. It's always going to be 1. So in the end, this will form into K NO2 to the second power. And we just assume that 1 is over here. Let's do a learning check based on what we have learned so far. The rate law for the reaction is H2 plus 2NO forming into N2O plus H2O. And it has already been experimentally determined to be rate is equal to K, and you see the NO to the second power and H2. What are the orders of respect to each reactant? And what is the overall order of the reaction? So for the NO, the order is, and you see the exponent is 2. For H2, what do you think the order is? Order is not 0. If it was 0, then that H2 wouldn't even be there. It's actually 1, but it's not showing the exponent 1. So the overall order, you're just going to add 2 plus the 1, and that would be 3. Try the next rate law learning check on your own and come back to check the key. And here is a key. You might have to note that CH3OH, that's methanol, and this long reactant, that's ethyl acetate, and that is 0 order, and that's why you don't see it over here. Anything to the 0 power is just 1. So overall, 1 plus the 0 is 1 order. Now, you'll probably notice that there is that K right there. That K represents reaction constant, and I haven't really introduced too much about that, and I will more in the later videos. But I want you to know that the K actually has a unit, and it really depends on the overall reaction orders. So if the overall reaction order is 0, then that K unit is molarity per second. If the overall reaction order is 1, and then it's 1 over second, or second to the negative 1. If it's 2 reaction order, then you have 1 over molarity second, or m to the negative first and s to the negative 1. And third, 1 over m to the second power multiplied by s, or m to the negative 2 and s to the negative 1. This you could find in your reference sheet, and I highly recommend you just keeping it. What about for reaction order 4, 5, 6, 7? Yes, those are available and you can solve them out, but for the scope of this class, we'll just end it with the reaction order from 0 to 3.